Okay, so the plan for today is to start chapter 7 on confidence intervals. Right before class, I made available the chapter 6 supplement, that just those last couple of topics on chapter 6. I posted that on YouTube in the same playlist as all of our class lectures. So they're just the next two lectures. There's a part 1 and a part 2. So those are up and available now. Those last couple of sections in chapter 6 are due this coming Sunday. And then we're starting chapter 7 on confidence intervals. We started that a little bit already last time, talking about things like estimators and so on. But we're going to continue with that today. The quote of the day today, it's a fun day today. We have the eclipse, obviously. We also have the candidates tournament for the World Chess Championship going on right now. So it's the tournament where the some of the top players in the world will play against one another to decide who plays Ding Liren for the title of World Chess Champion. So in honor of that, I have two chess quotes. So from Emanuel Lasker, the second World Chess Champion in the early 1900s, when you see a good move, look for a better one. And I think, kind of somewhat along these same lines from current GM Maurice Ashley, American GM. There are three types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, it's foolish. So I think both of these kind of get at the idea of when you're thinking of doing something to kind of fundamentally change the game, whether it's like trading pieces. If you trade your queen for your opponent's queen, the queens are off the board now for the rest of the game, I suppose, maybe until a pawn promotes way later in the game. But when you're fundamentally looking at changing the nature of the game, give that a lot of thought. And I think the same thing goes for life in general, that when you're fundamentally looking at changing, your life, whether that's accepting a job or deciding which job offer or any number of things decisions you have to make throughout your life, maybe it warrants giving that a lot of thought and not just doing something because it's kind of the easy road, but asking if it's the right path or not. So maybe we should apportion our amount of time and effort that we give to a certain decision. Maybe we should apportion a proportionate amount of time and effort and cognition to this, I guess, severity in some sense of the decision. I don't know if that's exactly the right word that I'm looking for, but it's Monday. We'll just go with that. I wonder if an eclipse is anything like a full moon, where they say, like, everything kind of goes a little crazy in society on days that there's a full moon. Maybe it's the same with the eclipse. I don't know. But anyway, so moving on to confidence intervals. So recall from last week, it's been a few days. So just as a really quick reminder, we have population parameters and sample statistics. And the one we often think about is the mean. So we have a population mean. We would like to know the population mean, but we typically can't know that. We're stuck taking a sample and finding the sample mean X bar. And X bar is an estimate of mu. If you take a sample from the population, you compute X bar. If I ask you, what's your best guess at what mu is, you would say, my best guess is X bar. But that doesn't really tell us a whole lot, because we don't know if that's a good guess at all. It might be a terrible guess. It might be an excellent guess. We're not really sure. The first thing we would like to know is that the thing that we're saying is a good guess satisfies these criteria of a good estimator. And we talked a bit about this last time: the unbiasedness, convergence, and minimum variance. And we have a list of some good estimators. X bar is a good estimator of mu. S squared, the sample variance, is a good estimator of sigma squared, the population variance. P hat, the sample proportion, is a good estimator of P, the population proportion. Unfortunately, S, the sample standard deviation, is not technically a good estimator of sigma, the population standard deviation. But for our purposes, we're taking it to be a rule of thumb that it's good enough in most cases. So we are kind of just pretending that S is a good estimator of sigma. Maybe I shouldn't say pretending, but we're saying it's good enough for our purposes. We're taking it as a rule of thumb, even though it technically does not meet these criteria up here. Okay, so let's work now on the simplest case where we're trying to ask, how good is it? Remember, this was kind of the idea that, anytime that you are taking a laboratory science, physics or chemistry or something, you don't just do an experiment one time and, one run of the experiment and take your result and that's it. You should repeat that experiment several times. You're rolling a ball down a ramp or something and timing how long it takes. You do that a whole bunch of times, and then that gives you kind of an average time that, say, it takes to get on the ramp, as well as some idea of margin of error, some idea of what's the kind of minimum and maximum time that I saw, or maybe what's the standard deviation of times or something like that. And then you can get bounds on your estimate. You can say, here's my best guess, but also kind of how good do I think my guess is? Is it, 10 seconds to roll down the ramp plus or minus 1 second, or 10 seconds plus or minus 7 seconds? That's a big difference, even though it's the same best guess. So what we would like to do, we would like to construct what we're going to call a confidence interval. Instead of a point estimate, instead of a best guess, this is an interval estimate. And very roughly what it's saying is, instead of saying my best guess at mu is this number, I'm saying I'm a certain amount confident that mu is between these two numbers. There's a little bit of a technicality we'll have to discuss later on, but that's roughly speaking what we're trying to do. In other words, we're trying to compute L and U, a lower and upper bound, so that we can report an interval, the open interval from L to U. And we would like to say something like, my best guess from U is X bar, and say 95% confident that mu is in the interval L to U. How can I compute such an L and U? I'm going to do, oh, my line kind of cut off a little funky there. I'm going to use two criteria here. Number one, I'm going to leverage that for X bar, our best guess for mu, our estimator for mu, we actually can use the central limit theorem. We know that, at least under certain assumptions, we know that X bar is normally distributed with mean mu X bar equals mu and standard deviation sigma X bar equals sigma over root n. We're also going to choose to impose symmetry. We're going to choose to search for a symmetric confidence interval. X bar is our best guess for mu. It's a good estimator. It's unbiased. On average, X bar lands right on top of mu. There's no reason that I should have an interval that's not symmetric. There's no reason that I should go, say, twice as far to the right of X bar as to the left of X bar if I want to capture 95% of my distribution. It seems pretty reasonable to keep it symmetric because X bar kind of on average hits mu. So when I make an error, I want it to be as likely that I make an error by having an interval that's too high and I miss mu on the bottom side as vice versa. We will talk about one-sided confidence intervals a bit later, but for right now, we're dealing with two-sided confidence intervals. And again, we're going to impose symmetry. We're going to go the same distance to the left of X bar as to the right of X bar to get L and U. That distance to either side of X bar that we go, we name it E, and that stands for margin of error. Okay, so what does this look like then? Well, I know that my distribution of the random variable X bar keep in mind I'm thinking of X bar being a random variable here. If I took different samples from the population and computed the sample mean from different samples, I would get different results for that sample mean. So there's a distribution of X bar. It is normal with mean mu and standard deviation sigma over root n. That was what the central limit theorem said. Now to apply this, we do need a couple assumptions. We need a random sample. And we need n bigger than or equal to 30 or a normal population. That was the n bigger than or equal to 30 was our rule of thumb to apply the central limit theorem's conclusion. So X bar is centered at mu. Now from my data, maybe come back up here and say from my data, if I collect a sample from the population, I know n, I know my sample size. That's needed for down here. I also know my sample mean. I'm going to call this, because I've got a couple of things I want to call X bar now. I have the random variable X bar, this kind of abstract concept that when I take different samples from the population, I get different observed values of the mean. So that's a random variable. But for a particular data set, I get a specific mean. I'm going to call that X bar observed. So X bar subscript OBS. So this is the actual observed value of this random variable X bar that I got from a specific sample, from a specific data set. And now we're going to make an assumption that might seem a little strange, but we're going to assume sigma is known. Now you might say, well, wait, if we don't know mu, but we do know sigma, that seems kind of strange. And admittedly, that's not the typical case, but we're working on kind of a simplest case here. And then we're going to build off of that to see how does this change if we don't have the assumption that sigma is known and we just go off of S being an estimate of sigma. How does that change things? So we'll look at that kind of in the future, but we're going to start with this case, assuming sigma is known. So we're assuming we know the population standard deviation and our sample size and our sample mean from the data. But we, of course, do not know mu. If we knew mu, we wouldn't be giving a confidence interval for mu. We would just say what mu is. Okay, so I know sigma and I know n, so I can find root n. So I know sigma X bar. My goal here is to come up with an upper bound and a lower bound where, say, maybe the area between them is 95% or whatever other confidence level I want. I'm just going to use 95% here as kind of an example, but we could find a 99% confidence interval or 90% confidence interval. They're both pretty common. We could, in theory, find a 93.5% confidence interval or an 87.4% confidence interval. So we could set whatever confidence we want, essentially. But 95% is definitely the most common. 90 and 99% are probably the next most common. So there are kind of pretty standard confidence intervals that tend to come up. But we use 95% as an example. Okay, so if I have my distribution X bar, I'm looking for L and U. I'm looking for the middle 95% of this distribution. I have a bit of an issue here. The issue is that this distribution is centered at mu. I need to know the center of the distribution to know what L and U are, but I don't know mu. That's kind of the whole thing that I'm trying to find. But I do know that my best guess at mu is X bar observed. Effectively, what I can do is I can just replace mu with X bar observed. And say X bar observed is my best guess for mu. That's maybe kind of the gut feeling reason that that works, is that X bar observed is my best guess for mu. It's as likely to miss above as below, so that shouldn't really bias our results at all. There is a string of technical calculations that can be gone through to show that this actually, this gut feeling idea does actually work. And kind of roughly speaking, X bar observed minus mu is also going to be normally distributed with very similar parameters. Kind of think of the word for a minute. So that's really where this comes from. It comes from the fact that things like adding or subtracting a number to or from a normal distribution doesn't fundamentally change in the distribution. The difference of two normal distributions doesn't fundamentally change the distribution. So things like that. So we're going to instead center this distribution at X bar observed. And I'm just going to come over here and replace that. And now I have a normal distribution with a mean and a standard deviation that I know from my data or my assumptions. And I'm looking for the middle, say 95% of that data set. How do I go about finding this? Well, one thing that I can realize is because of the symmetry, so X bar observed is the mean, it's in the middle. The distribution is symmetric about X bar observed, but also L and U are symmetric about X bar observed by construction. Everything is nice and symmetric here. That also means that the tails are also symmetric. These tails are the same size, even the same shape, just mirrored. So if I have a confidence level of 95%, if I have 95% in between L and U, that means I have to have a total of 5% combined between the two tails. Or that tells me that I have to have 2.5% in the left tail and 2.5% in the right tail. Now let me come over to a standard normal. And if I'm looking for a standard normal index or indices with 2.5% in the right tail, that's what I call Z subscript 0.025. That's the Z index with 2.5% area in the right tail. And then I notice by symmetry that the left tail, it's going to be associated with a Z index of negative Z subscript 0.025. And again, I know that my L and U are related to these Z indices through the Z score. So the Z score is X minus the mean over standard deviation, or here I'm going to say X minus mu X bar over sigma X bar. And I want to solve for the X index, U or L, in terms of Z. So I'll use this rearrangement of my z-score. Or I see that, trying to get this all on one screen, but I can't quite do it. I see that, for instance, the upper bound, is the mean of the x bar distribution is going to be x bar observed plus the z-score I'm interested in, z 0.025. It's 1 minus the confidence level, and then half of that, times sigma x bar, which is sigma over root n. And then my lower bound is going to be essentially exactly the same. X bar observed plus, but now I use my left tail z index, negative z 0.025, but typically we don't write that as plus or minus z. Typically we'll just write it as minus z sub 0.025 sigma over root n. And these would be our formulas for the upper and lower bound. When I look up z.025, I'll do that on my normal table over here, looking for a z index with 2.5% area to the right, or that's just negative of the z index with 2.5% area to the left. And again, remember, I know x bar observed from my data set. I can find z.025 from my z table. I know sigma by assumption. And I know n from my data set. That's just the size of my data set. So I know all of the pieces here. If I have a data set, I could compute all of these pieces and get my confidence interval. One last note is, remember, we wanted L to be like x bar minus margin of error, U to be x bar plus margin of error. And we see that this is true. X bar observed plus E and x bar observed minus E, where my margin of error is z.025 sigma over root n. So I have a confidence interval that's symmetric about my point estimate, my best guess, my good estimator from U, with a margin of error that's given by this, z.025 times sigma over root n. Now, I did all of this for a 95% confidence interval just because there's already a lot of symbols floating around. But what if I wanted a 90 or a 99% confidence interval? Or what if I wanted a, say, p% confidence interval? So here p might be 95, or p might be another number like 99 or 90. Well, all that changes is my tail areas. This is going to be what? Well, this is 100 minus p%, and then over 2. So if I have 95% in the middle, I have 100 minus 95 is 5% total between the two tails, and then half of that in each tail. Now, typically, I just call the sum of these two areas alpha. It's the error rate. So the sum of these is typically just called alpha, the error rate. In other words, the percentage of the time that my confidence interval misses the true mean, that the true mean does not end up being between L and U, that it ends up being located out in the tail somewhere to the left of L or to the right of U. So alpha is 1 minus p%. It's the error rate. It's the percent chance that my constructed interval does not cover the mean. P% of the time it does cover the mean, alpha proportion of the time it does not. So then I really just have alpha over 2 area in each tail. So I don't have to do this whole like 100 minus p% over 2 business. We just call it alpha over 2 area in each tail. And if we track the changes down, really all that changes is the subscript on these z's. So it's just z subscript alpha over 2 for a general confidence interval. Note that this is z subscript alpha over 2, not z alpha over 2. We're not finding z alpha, then dividing it by 2. We're taking alpha, the total error rate, the total area combined between the two tails, dividing that by 2, then finding the z index. So just make sure to keep that straight. Okay, so here I have it written out, kind of typed out. So my lower and upper bound again is x bar observed plus or minus a margin of error that's z alpha over 2 times sigma x bar, where sigma x bar is just sigma x over root n. Now there is one detail that I kind of skipped over here. What we'd really like to say about an interval like this, I'd really like to say something like, I'm 95% confident that mu is in the interval L to U. That's kind of the motivation that led me down this path, that I wanted to say something like that. Can I actually say that? Unfortunately, the answer is kind of no. Why is that? So we might want to say something like, there's a 95% chance that mu is in this interval. But if we make a statement like that, we're really stating that the interval is fixed and mu is the random variable. Unfortunately, well, maybe not unfortunately, but we're working in frequentist statistics, not Bayesian statistics. And this statement is fundamentally Bayesian. What a frequentist would say is, well, mu isn't random. We've decided what our population is. We say this, whatever, if we're talking about heights of people in Pittsburgh, this is our group of Pittsburghers at this time. Our population is what it is. It's set. If I was omniscient, I could know what mu was. Mu is fixed, but we just don't know it. So we can't say that there's a chance that mu is equal to this number or that mu is in this interval or whatever. The frequentist would say it either is or it isn't. We just don't know whether it is in that interval. Mu is not random from the perspective of a frequentist, because the frequentist says, once you decide your population, mu is fixed, you just don't know what it is. The Bayesian, who interprets probability more along the lines of degree of belief or information that I have or something along those lines, the Bayesian has no problem saying that mu is random, because it's all about my subjective probability. From my perspective, I still don't know what mu is. If I have 100 of these situations where I have some population I'm trying to find the mean of, if I make guesses about the mean, sometimes I'll be right and sometimes I'll be wrong. So we can treat kind of the mean as a random variable in the Bayesian world, but not in the frequentist world, which is where we are firmly entrenched right now. So if we wanted to make a statement like this, that's fundamentally Bayesian. There's a funny little quote. I think it's by Dennis Lindley, a Bayesian statistician, who says something like, inside every non-Bayesian, there's a Bayesian struggling to get out. And this is kind of why, is that one of the really big benefits of the Bayesian perspective is language that we want to use like this, we can use. The language used in the interpretation of the Bayesian equivalent statements is much more natural. But what does the frequentist say? The frequentist says, okay, what is actually random here? In other words, of all of these things up here, what changes under repeated sampling? In other words, if I got a certain data set of size n and I computed x bar observed for my data set and you did the same, you got a different data set, a different random sample from the population, and you got a different x bar observed, well, what changes is actually u and L. So actually L and U, the upper and lower bounds of the confidence interval, these are random variables. It's kind of strange. It's like x bar is a random variable, and that's why we're giving a confidence interval. But actually the bounds of our confidence interval themselves are random variables. They would change if I got a different sample and got a different x bar observed, I'd get a different L and U. So these L and U are actually themselves random variables, but mu fixed, not a random variable. Again, from the perspective of the frequentist philosophy. This is why I think it's important to kind of understand a little bit the difference between Bayesianism and frequentism, aside from some of the use cases that we talked about before. It really helps you to understand why we have to jump through some of these hoops when we're dealing with confidence intervals and especially hypothesis testing. So L and U are actually the random variables, mu is fixed. So we really need to say make our statement in kind of the opposite way of what we wanted to up here. The frequentist would say something like this: there's a 95% chance that an interval constructed using the process outlined above would cover the true mean mu. It might sound like these are the same statement. There's a 95% chance mu is in the interval versus there's a 95% chance that the interval covers mu. But again, the detail is that here we're talking about the chance that an interval does something. The interval is being treated as random, and the event is that it covers mu. Mu is being treated as fixed. Here we're talking about mu being the thing that's random, and the event or the fixed criterion is the interval L to U. So we need to actually interpret these confidence intervals this way. The chance that that an interval constructed using this process covers mu, that's what the confidence level gives us. Now, to be fair, if you said this to somebody and you consider what mindset that would put them in, what they would think or understand or whatever about this thing you're describing to them, versus if you said this to them, it's probably going to be basically the same thought process and mindset unless they're a statistician. These two statements, these two quotes here, are probably going to lead the vast majority of people to think the same way about whatever it is that you're telling them. So this nuance, while an important technical detail in some sense, may be unlikely to change somebody's perspective on what's actually being said. But the thing is that once we get into chapter 8, there will be similar discrepancies like these that are much more serious, that are much more grave, where if you say it one way versus the other, what the person thinks is going to be very, very different. So we want to get used to saying things the correct way in chapter 7. Then when we get to chapter 8, hypothesis testing, it'll be a little bit easier to say things the correct way there. The unfortunate thing about these frequentist inferential techniques is that it always feels a little bit backwards. It always feels like we're kind of tripping over ourselves in how we have to word things. And And even me, after having taught this course for over 10 years now, um, every once in a while I'll slip up and say something slightly wrong and have to correct myself. Or so we do have to be really careful how we interpret these. And that is a downside of frequentist statistics, is the interpretation, is saying, when I report this mathematical thing, it's like, okay, that's maybe nobody questions the mathematics of what this confidence interval lower and upper bound are, but what does that actually mean? That interpretation is I think typically more difficult in frequentist statistics than in Bayesian. But that's something we just have to be careful about. We have to be extra careful with the interpretation of things in chapter 7 and 8. Okay, let's come back to this. That was a lot of theoretical discussion. Let's go through an example. So here we have example 1. The administration of a certain hospital would like to know the mean noise level in the hallways. So, obviously, if you're in a hospital, people are trying to rest and recover. If the hallways tend to be noisy, people are constantly getting woken up, right? So we might be concerned with this. We want, on average, quieter hallways. They take a random sample of 84 readings, find a sample mean noise level of 61.2 decibels, and we assume the standard deviation is known to be 7.9 decibels. Maybe we assume that from maybe we have access to studies of a whole bunch of hospitals, and we can pull the standard deviation from there and presume that ours is maybe about the same. And we would like to compute the 95% confidence interval for the true mean noise level in the hallways. And so again, our formula for the confidence interval is this: X bar observed, the X bar that we got from our data, plus or minus our margin of error, which is Z alpha over 2, sigma X over root n. So I like to always start these problems, either in chapter 7 or chapter 8, with saying what we know and what we don't know. I don't know mu. I do know n. N is 84. I note that this is bigger than or equal to 30, so I can apply the results of the central limit theorem. I can use the constructed confidence interval. I've met that assumption. I know X bar observed is 61.2. And I actually do know sigma here is 7.9. I also know my confidence level. Confidence level is 95%. Now, it might seem kind of silly at this point to write out what we know and don't know, but we'll see as we go through. Sometimes there are other pieces of information we don't know, particularly if we don't know sigma. That might be something that we would want to note. That'll indicate that we need to use a slightly different confidence interval. Okay, but I see that I can use this confidence interval. I've met the assumption. So my lower and upper bounds are centered around X bar observed, 61.2, minus or plus my margin of error. I have some Z number that I'm going to find in a second here, times sigma X over root n. So times 7.9 over root 84. Now, the last thing I need to find is my Z number. So if my confidence level is 95%, that tells me that alpha is 5% or 0.05. That's the total combined area between the two tails. Or alpha over 2 is 0.025, 2.5% area in each tail. So I need to find Z 0.025. Let me come over to my normal table here. I want to find the Z index with 2.5% area to the right. My table gives me areas to the left, so I'm going to find the Z index with 2.5% area to the left, and then just take its negative to get the Z index with 2.5% area to the right. I'm looking for 0.0250 on here, and I actually find it right on there. So 2.5% area, 0.0250. I find that number correct to 4 decimal places right here on the table. And I see that's associated with the Z index of negative 1.96. So 2.5% area to the left of negative 1.96, or 2.5% area to the right of positive 1.96. So that's my Z number that goes here and here. I think this table even, no, it's actually not on this table. I think, oh no, there it is. So this table even has a nice little chart in the bottom here. It's only on the bottom of one of the sides. For these common critical values, we see for confidence level 95%, this gives us a Z score, a Z index of 1.96. So there's a little kind of quick lookup table here for the most common confidence levels, 95, 90, and 99%. And now I just need to compute these two numbers. Let me bring up my calculator. So I need 61.2 minus 1.96 times 7.9 over square root of 84. And that looks good. So this gives me 59.51. I go with 59.5 because these all seem to be rounded to 1 decimal place. And then I do the same thing with a plus, so I'll just do second enter. And then just change my minus to a plus, hit enter again. This gives me 62.9. And I can say that my 95% confidence interval for the mean is the interval 59.5 to 62.9. And I would say that the interpretation of this is that I'm 95% confident, I'm 95% certain, there's a 95% probability that the interval 59.5 to 62.9 covers the true mean mu. Okay, let's look at another example. So here we have a publishing company wants to know the average price of novels on the market. And we'll assume that prevailing market knowledge suggests that the standard deviation of the price of novels on the market is $3. So we know sigma. We take a sample of size 25. We see that a sample mean X bar observed of $14.5. That's what we observed from our sample. And we assume normality of the underlying population. Note that because we have a sample size that does not meet our rule of thumb of being at least 30, the only other way we can apply the result of the central limit theorem and be free to use our confidence interval calculation is if the underlying population is normal, and here that is assumed. And we want to construct the 90% confidence interval for mu, the true mean price of a novel. So again, let's just write out what we know and don't know. Well, of course, we don't know mu. If I knew what mu was, if I had access to the whole population and just knew mu, if you said what's mu, I would just tell you the number that mu is. I wouldn't have to do all of this estimating and confidence intervals and stuff. So we don't know mu. We do know our sample size, 25. We do know our estimator for mu, our best guess. X bar observed, 14.5. We do know sigma of 3, our population standard deviation. And we do know our confidence level, 90%. So 90% area in the middle of the distribution, that means 10% error, so to speak, or 10% area combined between the two tails. And alpha over 2 is 5%. And I think this is what I have saved there, yeah. So we can just pop our same formula down here. Again, we know we can use this formula because even though 25 is less than 30, we have a normal underlying population. We can use the result of the central limit theorem and therefore use our confidence interval formula. My lower and upper bound, again, both center around X bar observed. And here I'm going to do things a little differently than the way I did them before. Just a different choice. You could do it either way. I'm going to compute my margin of error separately. And then I'm just going to get whatever my margin of error is and plug it in up here. So my margin of error is going to be some number. It's going to be z 0.05 times the standard error, sigma x over root n, or the standard deviation of 3 over root 25. Z 0.05 is the z index, the standard normal index, with 5% area to the right. And to find that, I come over to my z-scores table. I can find the z-score with 5% area to the left, and then just take its negative of that index. Or again, another way that I could approach this, so that would be like using symmetry. Another way I could approach this is if I said, well, 5% area to the right means 95% area to the left. This is just the 95th percentile. So I'm just giving you a couple different ways to approach different aspects of these problems. You can choose the way that you like the best. But if I'm looking for the 95th percentile, I'm looking for an area to the left of 0.9500. And it falls right in between these two, which we see corresponds to a z-score of 1.645. We could also see that over here, the confidence level of 90% corresponds to a critical value of z-score of 1.645. I could compute my margin of error. 1.645 times 3 over, well, square root of 25 is just 5. This gives me 0.987. And then I can take 14, wrong screen. I can take 14.5 minus 0.987. This gives me 13.5. I guess I'm rounding to one decimal place. This just ends up being 1. But then I can do the same thing with just a plus is what, 15.5. And I can say that my 90% confidence interval from mu is 13.5 to 15.5. And the interpretation would be that I'm 90% confident that the interval 13.5 to 15.5 covers the true population mean mu. As kind of an aside, what are the units of lower and upper bound? Well, I know that my X bar observed, that's in units of the original data in dollars. My margin of error is just a Z number, that's just a unitless number. I have a 1 over root n, that's just a unitless number. And sigma is in units of my original data as well. So my margin of error is also in units of my original data. I have the sum or difference of units of my original data. My lower and upper bound are in those same units. Right. That's pretty nice to know, right? It's good to just kind of check these things. If I was trying to like take dollars minus a unitless number or dollars minus dollars squared or something, that would be an indication that something somewhere went wrong. Any questions so far? Okay, so what have we done so far? We've constructed a confidence interval for mu when sigma is known and come up with a formula for it, wherever our formula was. I guess it's down here. We'd seen before that if we can say something about mu, the mean, that kind of gives me a statement about the proportion or probability of an event for free. And we talked a bit more about this last time and a lot more in previous work in chapter 5. But we can say from our central limit theorem for P, population proportion, or really for P hat, we can say that P hat, our sample proportion, is normally distributed, where the mean is with a mu of P hat and a standard deviation of root P hat 1 minus P hat over n. Here I've just replaced, before we said these were P, here I replaced P with P hat for essentially the same reason that I replaced mu with X bar observed here. So we can construct a confidence interval for population proportion P, or probability of event P, in a similar way, right? We have the same structure underlying everything, so our confidence interval is just going to be point estimate plus or minus margin of error under the same symmetry conditions and so on. Our margin of error is going to be a z-score because we're dealing with a normal distribution. Z alpha over 2, that stays the same, times the standard error. The standard deviation of P hat is this whole big square root thing here. Right, this is like root P times 1 minus P, which is the standard deviation of kind of the underlying binomial distribution or Bernoulli distribution, and then divided by square root of n. But when I have a square root over a square root, I can just put that all under the same square root. So that's all that I've done here. And again, we talked a little more about this back in chapter 5. We talked about it in the central limit theorem section. So refer back to that if this is not looking familiar. But essentially everything is the same, except we have P hat, or sample probability of success, instead of X bar observed, and we have a different looking standard error. But otherwise the structure and the basic ideas are the same. Okay, so let's look at problem 3 here. Suppose we roll a 6-sided die 100 times and we observe 21 ones. We'd like to compute a 95% confidence interval for P. The true probability of rolling a 1 on this die. And then we might want to answer a question, does it seem plausible this die is fair? So maybe we're in quality control for a dice manufacturer, and we want to see if, we're going to roll a die 100 times. Of course, we're not going to get exactly 1/6 of the rolls coming up ones. Number one, that's impossible. We can't get exactly 1/6 of 100 ones. 6 doesn't go evenly into 100. But even if it did, even if we rolled a die 120 times and it was a perfect die, I know just by sampling error, just by chance variation, that I might get a few extra ones in this sample and a few fewer ones in this other sample, even if it's a perfect die. So that's why I want to look at not just the point estimate of 21 ones. I mean, okay, that's a little higher than I might expect on average for a fair die, but is it kind of within the realm of kind of reasonableness for a fair die? So that's ultimately what the question that I want to answer here. Okay, so what pieces do I need? Well, I need p hat observed, or this is the observed number of successes, the observed number of ones rolled over the number of trials. Or this is 21 over 100, or 0.21. I know that n is 100. I know my confidence level is 95%, which tells me that alpha, so 95% confidence, 95% of the time I'm going to generate an interval that covers the true population parameter. 5% of the time I make an error, I generate an interval that does not cover the parameter. So here alpha over 2 is 0.025. My lower and upper bound, I get by p hat observed 0.21 minus or plus. I need a z number. I'll find that in a second here. Times my standard error. So what is this bit? This is going to be root 0.21. 1 minus 0.21 is 0.79 over 100. So that all is going to go here. So here, what I think I'm going to do for, just to make the calculations a little easier, I'm going to choose to go the route that I did up here, where I compute margin of error separately and then plug in. So I'll compute my margin of error as a z number times square root of 0.21 times 0.79 over 100. Figure out what that is, and then substitute that number in up here. So what's z 0.025? Again, I could find 0.0250 area to the left. That gives me a negative z-score, and then just flip the sign to positive. I could find 0.9750, noting that an area to the right of 0.025 is equivalent to an area to the left of 0.975. Or I could look at my little table down here. I know this is a 95% confidence interval. This tells me the index I'm looking for is 1.96. Any of those ways would get me this 1.96. So I need to go about 2 standard errors in each direction. So I need 1.96 times in this big square root, 0.21 times 0.79 over 100 n to the square root. So that all looks good. I don't need any parentheses inside the radical because 0.21 times 0.79 are in the numerator, and then divide by 100. The numerator is all multiplied, so that's fine. Don't need any extra parentheses. This gives me 0.0798. I do have a couple of decimal places of accuracy here, so maybe I'll go out to 0.0798. Maybe I'll go all the way out to there. And then I want to do 0.21 minus 0.0798. Give me 0.1302, or we'll just call that 0.13 for the lower bound. And then the upper bound is just the same calculation with the minus turned into a plus. 0.2898 or 0.29. This is a 95% confidence interval, so we'd say the 95% confidence interval for P, or the probability of rolling a 1, is 13% to 29%. Or in other words, we are 95% confident, 95% certain that the interval 13% to 29% covers the true population proportion probability of rolling a 1. And now to take it even a step further, does it seem plausible that this die is fair? In other words, 21 1 seems a bit high. I would have expected maybe 16 or 17 on average. 21 ones is a bit above what I expected, but is it so far above that I would say, I think that's unlikely to have just occurred by chance, and that I think the die is fundamentally flawed, that ones are fundamentally coming up too high. Well, I note that my perfect die would roll a 1 1/6 of the time, or about 16.7% of the time. And I noticed the 16.7% is in this confidence interval. It is between 13% and 29%. So I don't think this sample has such a high number of ones that were rolled that it is unreasonable this die is fair. So I would most likely say, okay, these are a little high. This 21 ones is a little higher than I'd expect, but not so high that I conclude the die is fair. And I would conclude the die is, maybe I should say I would not conclude the die is unfair. Maybe is the best way to say it. This gets a little bit into that kind of backwards frequentist logic that we'll see a lot of in chapter 8. But this is really kind of teasing a bit of chapter 8. So because we see 16.7% in the confidence interval that we came up with, we say, okay, it's plausible that 1/6 or 16.7% could really be the population proportion probability of rolling a 1 for a fair die. So we do not conclude the die is unfair on the basis of this sample. Okay, any questions? Any questions so far? Okay, so let's look at another example, problem 4 here. So let's suppose we're interested in knowing P, the probability that a voter votes for candidate A in an election. Some exit polling conducted between 3 p.m. and 4 p.m. on election day reveals that 539 out of 979 people polled voted for candidate A. So we want to do a few things here, but the first thing is let's construct a 99% confidence interval for P. So here P is probability voted for candidate A, and This is our formula, so we need p hat observed. Our observed sample probability of voting for candidate A is the number who voted for candidate A, probability of success or number of success, 539 over n over the total number sampled, 979. And let's figure out what that is. So that's about 55%. We also know n, 979. And we know our confidence level is 99%. Says that alpha is 1% or alpha over 2 is 0.005. Be careful with the number of zeros there. Alpha over 2, 0.005. And again, I think I'll probably compute E, the margin of error, first, and then do p hat observed plus or minus E, just because the margin of error is a lot to write down and I'd rather not write it twice, risk making a mistake. So my margin of error, well, that's going to be Z 0.005. Again, kind of three ways I can find that. I can look up 0.005, being careful to get 2 zeros there on my table. So area to the left of 0.005 corresponds to a Z index of negative 2.5, well, negative 2.575. And then since I'm looking for an area to the right, I make that positive 2.575. I could also say that 0.005 area to the right is the same Z index as 0.995 area to the left. 0.995 area to the left is right in between these two. That corresponds to 2.575 for the Z index. Or I could look at my little kind of cheat table down here, 99% confidence level, 2.575 for the Z index, the critical value as it's called. Either way, or any of those ways, gets me 2.575 for my Z value. Times the square root of p hat observed, 0.55, times 1 minus p hat observed, 0.45, over n of 979. So it's not the nicest calculation ever, but we just plug it into the calculator. 2.575 times square root 0.55 times 0.45 over 979. We don't need any other parentheses other than what's keeping all this stuff inside the square root. And that gives me a margin of error of 0.04 or so, about 4 percentage points. If you ever, watch the election coverage or anything like that, when they're talking about the stats, they'll say our estimate is blank. And usually there's a little, tiny note at the bottom that says like margin of error plus or minus 3 percentage points or something like that. That's what this means. So here we would say the margin of error is 4 percentage points. Basically, it means that our guess is 4 percentage points in either direction of our best guess. So my lower and upper bounds of the confidence interval are my point estimate, 0.55 minus or plus 0.04. So my 99% confidence interval for P, not mu, is 51% to 59%. Or I'm 99% certain that this interval will cover the true population proportion P. Okay, so let's consider maybe what we would, for parts B and C, something a little more qualitative, how we would want to actually use this. And, I always want to draw a line between when we say this statement is certain, this is an absolute truth, everything that we've done here is absolutely true. This is based on the mathematics. This is, unquestionable, but these next couple, you could maybe argue it either way. But let's look at some of the arguments. So simply considering the statistics, the numbers we calculated, on the basis of the exit poll, can we call the election for candidate A? So if I just look at these numbers here, I probably would be comfortable calling the election for candidate A. Again, roughly speaking, what I'm saying, not exactly right, but roughly speaking, I'm saying that I'm 99% confident that the candidate A is going to get between 51 and 59% of the votes. I mean, that's more than 50%. So roughly, I'm saying that I'm 99% or more confident that candidate A is going to win. So just looking at the numbers, we probably can say, yeah, we can call the election for candidate A. Just looking at the numbers, just the statistics, do we care what the population size is? Do I care if this is 979 voters of a small town mayoral election with, 5,000 people in it, or whether it's 979 voters of the presidential election with, well, I was going to say 320 million, but, there's a bunch of kids and people, I don't know. So let's say maybe 180 million voters. Just according to statistics, no, we don't care. Remember that our confidence interval up here, either one, we said nothing about the size of the population. The size of the population does not come into question or does not come into play to answer the question, how good is our estimate of the mean? It's only the size of the sample. We don't care about the size of the population, whether we're estimating a population of 100 or 1,000 or 1,000,000 or 1,000,000,000, it doesn't matter. So purely based on the numbers, do we care what the size of the population is that we have a sample of 979? No, we don't. Purely based on the numbers, can we call the election? Sure. Whether it's the presidential election, a small town election, doesn't matter. Just based on the numbers, we can definitely call, maybe not definitely. I think most would agree that we could call the election for candidate A. But something more qualitative, though, should we call the election on the basis of the sample? In other words, not just looking at the numbers. Does it make sense to call it? Well, here's where we would have to take some of the qualitative considerations into play. Does it matter what the size of the population is based on what we should do? Does it matter according to the calculations? Well, no. But do I think 1,000 people can give me a representative sample of 300 million or 200 million or whatever? I'm a lot more skeptical of that, right? Is my sample representative? Specifically, is a sample taken between 3 and 4 p.m. representative? Well, is that the same contingent of folks who are going to vote in the morning or in the afternoon or the evening? Probably not. Right? Are there other considerations that I should take into that I should try to account for? Perhaps. Right. So this is the qualitative side of statistics that, people can agree on the calculations, they can agree on the formulas, they can agree on these numbers, and they could still disagree. Very smart, well-researched, and well-meaning people could come to two completely different conclusions because one says, maybe in a certain context, this isn't a big enough sample to be representative. Maybe somebody else thinks that it is. Or I think that we're introducing selection bias into the sample by either the time slots or maybe the locations that were pulled or whatever. And another thinks that that's not the case. So what should we do on the basis of this? Well, that's a much more complicated question, right? That's a much more, I guess, slippery kind of question to answer. But coming down to question D, well, this is back to kind of the hard math question. What if we wanted a margin of error of at most 1 percentage point, assuming that p hat remains the same and for the same confidence level? I think we agree we would need a bigger sample size, right? If I want to be the same level of confident about a smaller interval with the same level of confidence with a lower margin of error, I need a larger sample. How big of a sample would I need to get a margin of error of 1 percentage point? Let's figure that out. So we're back to a math question now that we can answer unambiguously. So my margin of error is, well, if I change the sample size, does that change anything about z alpha over 2? No, it doesn't. It's still 2.575. If I assume that p hat remains the same at 0.55, these stay the same. But now I'm saying I'm changing the sample size. So instead of 979, I just have n. And I want my margin of error to be at most 1 percentage point, 0.01. What could I do here? I can solve for n by dividing both sides by 2.575, squaring. Let me do that. I can invert both sides. I have to be careful when I invert, that changes the direction of the inequality. And then I can multiply by 0.55 times 0.45. So if I invert both sides, the n is on top, bigger than or equal to, I get 0.55, 0.45 times 2.575 over 0.01 all squared. Does this kind of seem right? Well, sure, n is going to have to be bigger if 2.575 is bigger. If I'm further into the tail, or if I want to be more confident, I need a bigger n. That checks out. I also need a bigger n if 0.01 gets smaller. If I want a smaller margin of error, I need a bigger sample size as well. That also checks out. So it kind of, just the reasonability check seems like we did the algebra correctly. So I need 0.55 times 0.45, 0.45 times 2.575 over 0.01 squared. 0.55, 0.45 outside of the squared, and then 2.575 over 0.01 all squared. That looks right. So I need 16,411. So I need about 16, 17, something like that, times as many people to bring my margin of error from 4 percentage points down to 1 percentage point. And this does make sense, right? I know that my margin of error scales like 1 over root n. If I want to decrease my margin of error by a factor of 4, I need to multiply n by a factor of 16-ish, right? Approximately. I mean, this 0.04 wasn't exactly 0.04. That's why this isn't exactly 16 times, but because we scale like 1 over root n, if we want to cut by a factor of 4, we need to multiply n by 16. And that does check out here. We started with an n just shy of 1,000. And to get the smaller margin of error, 0.01, 1 percentage point, we need around 16,000. All right, are there any questions on anything we covered today? So the next topic then is going to be confidence interval from mu when sigma is unknown. This is probably kind of the more reasonable setup, right? Usually if we don't know mu, we probably also don't know sigma. This introduces a whole new set of ideas. So a new distribution, the t distribution, that's related to one of those PDFs that I posted in chat. So we're going to, I think, stop here. We'll stop a few minutes early, say it's in honor of the eclipse, but really we just, I think it's good to just wrap up here and not try to start the next big section with only about 15 or so minutes left. So we'll finish a few minutes early today. And then when we come back next time, we'll talk about